Hello guys, and today I have a video about AI agents. And today I won't be selling them to you. I won't be telling you that AI agents are amazing. Yeah, my purpose here is just to show you that any AI system, RAG system or chatbots, whatever, it's basically just a software as it was. Of course, it has some AI capabilities, it has some fancy LLMs, it has some orchestrator, harness, and stuff like that. But at the end of the day, it's just a software and it's still an engineering. So that's why I decided to prepare that video that explains the most relevant modules of any AI system. So first things first. As I mentioned, AI agents is a multi-module software. So what does that mean? That means that we have multiple layers here. You can see it's LLM, it's tools, it's orchestrator, it's harness. There could be any amount of those layers, but I decided to make this strict division, and I tried to highlight the most important ones. So let's start with the confusion. Sometimes people confuse LLM and AI agent, right? I talked about it already, but nevertheless. So how user sees any AI system? User types a message, right? Then we have this black box called AI, and then suddenly the answer appears, right? The AI searched the web, the AI sent the email, the AI remembered me, whatever. But what actually happens underneath? There is a module called harness, there is an orchestrator, there is a tools, there is an LLM, and all of these are really important for any production grade system, right? And here you can see the LLM, it's just the one piece of the system. And basically it's the reasoning engine here. But from my point of view, there are even more interesting layers, which are tools, orchestrator, and harness, and we'll be talking about it today. So first of all, the LLM never touches the outside. As mentioned, LLM is stateless reasoning engine which sits in the middle or deep inside your system. It takes the user input and produce the output on each iteration. So basically it's a box which accepts the context, user messages, the tool outputs, tool schemas, and all the context you provided. And this data goes through harness, orchestrator, and eventually reaches the LLM. Once again, the role of the LLM here is just to make a decision based on the context provided. The decision could be a tool call or direct answer. For example, LLM could decide that to address this intent, we need to do some more tool calls. So the answer would be a tool call. Otherwise, the model, the LLM here could decide that we are done, we fully covered our question, and the output will be the answer to the customer. In order to simplify it a bit, we could say that the agent runs the same 5 steps until it's done. The amount of steps could be different for sure, but these are the most common ones, and they reflect the approach of how modern systems designed. So here is the entry point. Step 1. The orchestrator assembles the context. We receive the message from the customer, we put it to some data array called context here for simplicity. Then we transfer it to the reason engine, to the LLM. Then we got a response from the LLM. Then it got parsed at the orchestrator layer again, exactly where it was assembled. So orchestrator does the parsing job. Basically, it extracts the actual response from the LLM. And based on that answer, we could decide at the orchestrator layer, once again, we can decide whether we need to call another tool or whether we're actually done with the execution. In case where another tool call needed, the orchestrator will invoke it. So requested tool call will be performed. A tool normally would return a tool result, right? And we can check it at the orchestrator layer again and decide whether we could proceed with the with this loop or we done And what is the definition of done here? Whether we completed the goal, whether we received the answer, the answer to initial user question, right? Or the termination could be because of the maximum amount of iterations reached. Or for example, if there's error during the execution. Anyway, there are still two possible ways, whether we can continue the loop or we could terminate the loop and return the answer to the user. So once again, step 1, we assemble the context, which could be passed to the LLM. Then we pass all the context we have to the LLM. LLM provides its reasoning and returns the response. Then we can either do a call or don't do a call and check the final outcome. And at this point, we can decide whether we will be proceeding with the execution of the loop or we can simply return the answer to the customer. Let's take a look on how it could be actually implemented in the real system from the customer perspective. Obviously, any system for humans has some visible user interface, right? So it's UI, it's front ends, it could be chat, dashboard, whatever. Then we have a processing layer as any backend system, because once we passed some data into the field, for example, into the chat, we need to pass it downstream into direction of the agent or database or whatever. So it's inevitable block of any AI system, which called orchestration, which basically means on how we treat these inputs from the user, how we treat it before it reaches the LLM. And you can see it could be event-driven processing, it could be some workflow, it could be some interfaces, it could be whatever. But the idea is that how we actually treat the context, how we treat the messages passed by the customers before it reaches the LLM. And then in any agentic system, we have an agent layer. And it normally includes the context assemble phase. It includes the creating of the client for communication with the LLM. So this layer contains all the necessary instruments in order to actually communicate with the language model. So again, usually at this model, we form our personality for the agent. We define the amount of loops. We can define conditions on how to navigate between the tools. Basically, at agentic layer, here we set the rules. We grant the personality to our agent, and we tell him what tools he could use. Then we have a memory and knowledge, and it's important for any software system, right? So in case of agents, obviously it would be some vector databases, embeddings, structured data, knowledge graph, whatever. So it's called state, and it's some persistent knowledge, persistent memory the agent could refer to. So it is the knowledge, this is persistent storage, which our system could use. Then we have APIs and external tools. And it's also same like for any software. Here we have search retrieval functionality, we have some action APIs, we have file input output, so we could call it as effects. So basically this reflects a business logic of our application. To make our agent alive, we have to make it reachable and accessible from the outer world, right? For that we could use some framework or runtime. So basically we need a server, and we need some backend server, and we need to expose an API of our application to the outer world. For that, we could use various of framework like Light LLM, we could use Fast API for Python. It could be anything, but the idea here is to expose your agentic system and make it reachable. And here you can see the telemetry. It's a relatively small block, but I find it really important because for any agentic system or for any software, it's crucially important to have sufficient monitoring and logging in place. Here you can see it includes such blocks as traces, metrics, audit logs. Basically, when something goes wrong or you have some malfunctioning on your application, you have to find and locate the exact layer which causes the cascade failures, for example. They will spend days fixing the failure. The idea of having this is basically to have the ability to understand what and where happened before the actual failure. Now, when we cover the core idea, I would like to make some deep dives into each layer, right? And the first one is the LLM, as mentioned, a stateless text function. So what it does, essentially it reads the entire context window on every call, it reasons, so it processes the input message array and produces some output. And normally this output is a text, which could represent a final answer or tool call. And then on the next iteration, it forgets everything between API calls. So normally LLM stores zero state, and it's our responsibility to handle it and to pass needed context to the LLM. Here on the right, you can see how it could be implemented in the code. I mean the communication with the LLM itself. So here we basically configure the client to the exact LLM, and here we have to specify the exact name of the LLM. We could pass some parameters in order to communicate with the LLM efficiently, such as max amount of tokens. An important part, it's the entire context to be passed to the LLM. And also, we have a dedicated tools parameter, which basically represents the toolset available for the LLM to call. So here, normally, after we configure the client for communication with the LLM, we have the checks inside the loop. And these checks serve pretty basic idea. So we just check whether we need to perform another tool use and continue the loop, or we are done. If we need to perform another tool usage, we will just get this from the last message produced by the LLM, and we will repeat another iteration. Otherwise, when we have already final answer, we will simply return it to the customer. And the context window we referred so far, which normally called messages array, it's essentially everything the LLM sees. So the context window we referred so far as messages is essentially everything the LLM sees. And normally it has these four sections like system prompt, conversation history, tool results, and current turn. Once again, the context window is basically a huge messages array which contains some structured data input to the LLM. It includes such structures like system prompt, which grants the personality to the agent in the scope of the current turn. Then we have a conversation history, so basically it represents everything we've been talking so far in the loop. And we also have tool results, which were called so far in the conversation, and we have a current tools in scope available for the agent to call in the next turn. And apart from this context, LLM doesn't have any other memory. Memory is whatever the orchestrator chooses to put in messages this turn. So it's up to you, and it's your design choice. Essentially the trade-off between the amount of data to be passed to messages and between the speed and also between the performance of the LLM. And everything here in the messages array costs you real money, because every token, every turn, the whole context is resent on every loop. So that's why it's really important to introduce some caching mechanisms. And every production grade system has multiple layers of caching, but that's completely another story. And I will be doing some video about it as well. So we will skip the caching so far, but you just have to keep it in mind. The next layer is the orchestrator, the agentic loop, and that's essentially a bit upper layer of abstraction above the LLM. And basically it receives a goal, the user input, it assembles the context, so it's aware of this context to be assembled and passed to the LLM. It actually performs the call to the LLM, so it serves as a client for the LLM. It also parses the response, so it deals with the raw response provided by the LLM. It also executes the tool In case when LLM decided to invoke the tool, the actual execution will be performed by the orchestrator. And it also injects the result, so it plays a key role in creating and maintaining the context. And eventually it also returns an answer to the customer. So as you can see, the orchestrator does lots of things, and it's a pretty important module. And here you can see the actual loop. It could be a for loop or it could be a while loop. Here we can see the maximum amount of iterations. So normally any loop has such condition, the maximum amount of iterations, regardless of whether we retrieved, whether we got the final response or not. So here, as mentioned, we create in the context, we pass it to the model. So the orchestrator here serves as a client. Then we append this response from the LLM to the context, and here we can check whether we can return the response and stop the iterations here, or we need to continue. So otherwise, where we still need to call another tool, we will append, we will basically say that the return of some tool is a result, and we will append the result of the tool to the context. So on the next iteration, we will be having all the previous conversation history and this exact response from the tool obtained on the previous call. So we just have to understand that orchestrator is basically a loop, and we'll be iterating through it until we receive a sufficient answer. So the next layer the orchestrator communicating with is tools. And here on the left you can see the tool schema. So basically it represents the available tool which LLM could interact with. So it looks like an API for the LLM. It specifies the name of the tool, it specifies the description, which is also really important and could give the LLM understanding of whether it should use this tool or whether it should not, how this exact tool should be treated, stuff like that. Then we have a parameters property, which helps the LLM to call this tool with the correct parameters. Which essentially contains the type, which is really important, and the name of the exact parameter to be invoked. And each parameter also has a description. And this field basically tells the LLM whether it's required for successful invocation or it's an optional parameter. So once LLM familiar with this schema, it could produce something like this, which is essentially an LLM output. Right, and it has a type, it is a tool use, it has an ID, it has a name, should be matching here, and it for sure should match the schema definition reflected here. So basically this is the request from the LLM towards orchestrator, which tells the orchestrator that LLM is intended to use some of the tools. Once again, LLM has no direct access to your backend API, to your code, and it only has this tool schema you defined. So this adds some additional separation level. And once the orchestrator receives this request, which could be treated as intent of the LLM to execute some particular backend code, it could proceed with the actual code execution. And this is basically your backend code here, implemented in Python. And once orchestrator received this intention of request from the LLM, it could perform the actual execution of this backend code, which actually performs the search and returns some JSON, which could be added to the context later on. And talking about the tools, I already touched just a bit this security topic when I was talking about the separation of the layers. Here you can see that our tools could actually invoke our state mutations, our database mutations. And it's critically important that the harness we are building is also capable to validate, authorize, confirm, rate limit the requests actually which we're receiving from the LLM. So the agent could be compromised and his tool executions could be malicious to your code. So that's why it's important to make a harness that way so it could validate every parameter against the schema. So for example, it should not be possible to pass some malicious code here, for example, or here. Also, it's considered a good practice to have some roles and grant some authorizations to your tools. So in other words, you have to grant least possible but still sufficient access to your agent. Let's take a look at a few more examples of how your harness could actually serve the security in your agentic system. So as you can see here, tool registry should be also implemented in a secure way. It should contain the information, which tools exist, which permissions each requires, which agent could call which tool. For example, circuit breaker implemented in your harness will prevent your system from some cascade failures. Human gate is another important module of your harness which should be implemented, because for some business critical or security critical operations, it's a must that a human should actually approve some actions. Also take care about your memory yourself, because you have to decide where you would like to store the logs, where you would like to store the context, because as we discussed before, the agent itself, the LLM itself is stateless, and in order to provide a state, to provide some persistent memory, persistent storage, we have to care about it. So we have to actually pick sufficient database. And it's not really that different comparing to other software systems, because we still have to decide what data source we would like to have, which access pattern we use, so which data structures we would like to handle. So memory is also important here, and design choices and trade-offs are really important here. So logging and tracing is kind of connected to the memory, because we have to also take care where our logs will be living, where we store it, what will be the retention policy, what will be the eviction policy and stuff like that. So it's still architecture of your system. And of course, the security boundaries could come also from the business side, could come from various directions, to be honest. So you need to have these boundaries and you have to keep them isolated. And now, once again, let's trace once again a real communication with the, for example, AI agent, right? So we have a user which has a goal which says, hey, research Stripe, right? Stripe is some payment gateway. So first we reach out the harness. Here we have all of our security checks. We can actually say whether this user has permission at all to retrieve any data from our agent. So here we can perform all security related or business logic related stuff. And once we authorized it, we can actually start our session with the orchestrator itself. And yet we're not communicating with LLM itself. We are just at the orchestrator layer. Here our loop begins. Here we assemble the context. We build this message array containing the agent personality, all the available tools, the message histories, right? And we pass it directly to LLM. For example, here LLM makes a decision that we need to perform a web search. It returns back to the orchestrator its response, which contains, it simply says that, hey, we need to perform a tool call. And orchestrator once again checks whether this LLM or whether this agent allowed to perform this exact operation, whether the parameters it passed match the existing API agreement. And only once it's confirmed and checked on the orchestrator layer, we could continue and perform the actual tool call. Our tool normally returns some successful response containing the desired results. In some cases, it could also return some error, and it's also important that error should be self-descriptive, so the agent could react on that, right? And in this particular scenario, we have that, okay, we need another loop, another iteration with this agent, because, okay, we actually search Stripe news for 2025, but we still need to fetch the Stripe version, and the agent for some reason decided to make it in two distinct calls. So we have another tool call, right? It's basically the same idea like here: authorization, tool usage, and response. And now we at the loop number 3. At this point, we have already all the context containing 2 previous successful calls, containing all the information, and we could add this data once again to the context and pass it again to the LLM in order to make it available for decision. So we're passing all this context with all the tool results, with all the history basically. And LLM, based on this, produces a decision that, okay, we're done, because this initial intent satisfied. So we simply return a text answer to the orchestrator. Here we actually can exit the loop and return the final answer to the user. And now let me show you some possible negative outcomes. For example, in case if you won't implement the harness, or if you implement it in a poor way, all right? So first of all, your AI agent or your system, which stores your sensitive data, will be actually vulnerable for some injections, like prompt injections or SQL injections. So you can name it whatever you want, but if you won't be checking on this, your system will be vulnerable. Another danger could come from the poor orchestrator design. For example, if you won't set the circuit breaker, some timeouts, some retries, some deduplication logic. So yeah, I think it's not really different to other software engineering systems, to distributed and loaded systems. So when your product, your agent, or your AI solution grows, so it scales, then you have to think about these ones more and more. That means that you have to think not about only positive use case or sunny day scenario, but also about negative outcomes and about failure mode of your AI system. Another good example could be a missing human in the loop. For example, you have some business critical operations and you definitely need the human to approve it first before the execution, and you did not set it up. So it could cause some business impact. And lastly, for any large scale system, you have to think about logging and monitoring. I would say it's one of the most important things here when you have some spreaded system, when you have some microservice architecture, or when you have some complex logic where you have some different interfaces involved. You have to think about it, how you would store the data, how you would store analytics, how you would access it, which monitoring tools you will be used, which traces you will be collecting, which metrics you will be, and how you will be transferring them. So there's lots of questions, and they're not necessarily related strictly to the AI topic, but still they are even more important when we're dealing with the AI systems. Today we have covered core models of any agentic system, and we saw how all the models communicate together, how they interact with each other, and why we need this complexity. I hope that will help you to understand the trade-offs and decision-making process throughout the implementation of any software solution. Thank you so much for watching this video. See you next time. Bye bye.